Hi, so our goal is to solve linear equations using properties of equality. And linear just means one-dimensional in this case. So you may notice that this is just an x here. We're not going to have x squareds or x cubes or anything like that, just one-dimensional. And you can have literal equations with two variables, that's fine, and functions. Those are all linear as long as they're just x's, right? Okay, so how would we solve an equation like this where there's a variable on one side? I want to talk just a moment about the concepts here. So the equal sign in this particular example does not mean like answer, and I think it's a common misconception. So this is not saying that 3x minus 5, the answer to that is 10 per se. I think a better way to think of the equal sign is that it's perfectly balanced. So we've got a balance here, and 3x minus 5 is on the left, right? Well, we can model that. We can make our x's. If you've ever used algebra tiles, the x's are kind of these rectangles. So we can say there's 3 x's on the left-hand side and 5 negatives. I'll make them negative with a negative sign. And on the right, there's 10 positives. So the question becomes, how can we isolate x to figure out what x must be to make this equation true and balanced? So x is a number that's going to have to make the left-hand side expression equal to 10 so that we can get 10 equals 10. So this thing will remain balanced. Right now it's perfectly balanced. And so first thing we might do is say, well, if we could just get rid of these negative 5s here, we could just be down to the 3 x's. And if we were going to get rid of these negative 5s, or sort of imagine taking them off the balance or off a scale, that's the same thing as adding 5. Just think about that concept for a moment. If someone was to say that getting rid of a negative 1 is the same thing as adding 1, that seems to make sense. So if we're at negative 1 and we get rid of that negative 1, we move up to 0, right? Well, if we're at negative 1 and we add 1, we move up to 0. So they're kind of equivalent ideas. So if we're going to get rid of 5 negatives, that's the same thing as adding 5 to both sides of our equation. And so when I cross these out or take them off, I'm going to have to add 5 to the right-hand side to keep it balanced. So 1, 2, 3, 4, 5. So I should have 15 on the right and only a 3x on the left. So 3x equals 15 now. Okay, but now I'm at a point where I know that 3 x's, so these 3 x's, because remember these are gone, these 3 x's are equal to these 15 1's. So that means that 1 x must correlate to a group of 5, right? Each x must be worth 5. Whenever you circle something and group it, it could be thought of as division. So in this particular case, I'll kind of move this down here. I kind of ran myself out of room. We're at 3x equals 15. What that would look like algebraically is dividing both sides by 3. So that x now equals 5. So these 3's cancel out and we're left with this x, and 15 divided by 3 equals that 5. And then if we were to plug that back into this x value to check it, 3 times 5 minus 5 does indeed equal 10, because that's 15 minus 5 equals 10, and 10 equals 10. So when we plug in what we said x equals, we get a true statement. Therefore, that's the balancing number. And that's really all we're doing when we're solving equations. Let's do one more example. I'm not going to use a balance this time. I'm going to talk a little bit more of maybe some of the traditional ways of writing them out and thinking of it. Okay, so again we have a perfectly balanced equation here because it's an equation, and we're going to find the value of x that would make it perfectly balanced. So on the left-hand side, I'm going to just kind of take note here. An equation is just really one expression being set equal to another expression. And I want to simplify expressions whenever I can. So I'm just going to simplify the left-hand side to 12. I can't combine the 3x and 9 on the right. But now I do want to get that 9 sort of out of my way and begin isolating x. So I'm going to do the inverse operation, that is the opposite of addition. Because positive 9 minus 9 is just 0. So 3x plus 0 is equal to, on the left-hand side, 3. Now that's a property of equality, the subtraction property. And that states that if a equals b, so you have a statement of equality, this balance, that a minus c is equal to b minus c. In other words, you're just allowed to subtract the same thing from both sides of an equation. It's just a fancy way of saying that. You're allowed to add the same thing to both sides of an equation. That's the addition property of equality. You're allowed to divide both sides of an equation by the same value and multiply. A lot of things you can do. You can square both sides, square root them. As long as you basically do the same thing to both sides, you're in the clear. So this is the same thing as 3 equals 3x. Now, it's pretty obvious here x equals 1, right? And you'll see a lot of mathematicians will then do the final step here of division. And it's because we're still trying to get x all the way by itself. And so 3 divided by 3 is just 1, and 1 times x is just x. So that's why we'll say that x equals 1 in this case. And if we were to plug it in to check it, which I always do, so we've got 16 minus, so I'll do a little line here so we can separate it, equals 3 times 1 plus 9, or 12 equals 3 plus 9, and then we end up with this true statement of 12 equaling 12. Okay, but what happens if we have variables on both sides? Let's take a look at one of those. So in this particular situation, we've got variables on both sides of the balance, of the equal sign. And I can't simplify the expression 4x minus 10, and I can't simplify the expression 15 plus 3x. So I'm going to go about combining things. It doesn't really matter what you combine first. You can combine the x's, you can combine the constants, the negative 10 and 15. But I did draw this picture down here to help us maybe understand it conceptually. If I've got 4x's on the left here, 4x, and I've got 3x's on the right, it's going to remain balanced if I take the same amount of stuff off of both sides at the same time. So I'm going to just remove 3x's, take them off the right, and take them off of the left-hand side, and that's going to look like subtraction. So you can treat these variable terms the same way you treat the numbers, and meaning that you can subtract them from both sides. That's not a problem. So 15 plus 0 now, because 3x minus 3x is 0, and x minus 10 is equal to that 15 plus 0. Now I need to deal with the values. So I've got negative 10 on the left, so I've got this negative 10 here, and I've got positive 15 on the right. So if I'm going to get rid of negative 10 on the left, because again, it looks like I'm trying to get all my x's to the left. It doesn't matter if you want all your x's on the right or the left. I just so happen to be working my way to get x's on the left here. I'm going to go ahead and get rid of these 10 negatives, which is the same thing as adding 10. So I'm adding 10 to both sides, so plus 10. And that's going to leave me with x is equal to 25. And I'll go ahead and draw those 10 here on the right. So 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So now I've got 25 numbers on the right. So that means in this case, x equals 25. But again, we want to check it, right? So 4 times 25 minus 10 is equal to 15 plus 3 times 25. Or 100 minus 10 is equal to 15 plus 75. And it looks like this would be 90 is equal to 90. So it checks out. X must be 25 in this case. So I hope this was helpful for you. And I'm going to go ahead and do one more example without the balance, just in case it's needed for people who are viewing. I'll do one more example with variables on both sides. So I came up with this problem, and there's so many ways to start equations, and there's so many right ways to go about it. It doesn't really, I guess it doesn't really matter how you want to start. There are certain things that you want to do first, but in this case, I'm going to go ahead and just add 5x to both sides straight off the bat here. You could have subtracted 13 from both sides. We could have added 12 to both sides. Anything we can do to kind of start simplifying. The goal is to get the x's together and get the non-x terms together. So now this is 0 plus 13 is equal to 15x minus 12. So now I'm going to go ahead and add 12 to both sides. And sure, I could have subtracted 13 from both sides, but that would have meant that I would have an expression on the right is equal to 0 on the left, and it's not exactly helpful. So 25 is equal to 15x because these canceled each other out, went to 0. So now when I divide by 15, I get that x is equal to 25 over 15, which is equivalent to 5 over 3, or 1 2/3. So in this particular case, x is equal to a mixed number or an improper fraction, however you want to think of it. And that's something that's important to remember, is x is definitely, there's no requirement that it's a whole number. And really quick, before I sign off, maybe I'll comment on this, because I can see why that might be confusing, this step here. So let me just hone in on that for a moment. So why when we get to this step of 25 equals 15x, am I dividing both sides by 15? Well, one way to think about it is this is 15 times x, and the inverse operation of multiplication is division. Another way to think about it is 15x, so before I divide, 15x itself is equivalent to 15 over 1 times x over 1. These are equivalent ideas. So if all of a sudden I'm saying, okay, I'm going to divide by 15, this right here, that right there is equivalent to 15 over 15 times x over 1, or 1 times x, which is just x. And that's what we wanted to do. We wanted to get x by itself. So anyways, good luck, and hope this was helpful.